back to studying Microbiology Chapter 2. Today's topic is electron microscope, and we are going to study the types of electron microscope as well. And this is reading, more like, understanding the concept with me and not more like teaching you guys, right? So let's start. Electron microscope. For centuries, the light microscope has been the most important instrument for studying the microorganisms, right? Like light microscope had 10 decades for studying the microorganisms, right? And at that time, the technologies were advancing, but it wasn't like that much advanced to say that the electron microscope would be developed. So it was in later 1900s that the electron microscope was developed. However, even the very best light microscope have a resolution limit of about 0.2 micrometer, which greatly compromise their usefulness for detailed study of microorganisms. Now, we know that we have studied the light microscope, but they are saying the best resolution, the limit of that is 0.2 micrometer. Guys, our eyes can see up to 0.2 millimeter, right? The light microscope, it take it further back into the numbers and make it 0.2 micrometer, right? But there are microorganisms that need resolution more than this, right? Even smaller resolution, you can say, not smaller, even smaller microorganisms than the 0.2 micrometer. So at that point, the light microscope doesn't work, and we can differentiate, like, if this is smaller or, larger. Viruses, for example, are too small to be seen with the light microscope. Yeah, that is the example. Wait a second. Wait. Let me see if this is working, so I don't need to, Oh my gosh, guys, my voice is way too strange. I didn't notice it. Wait. Let me go change the filter on that. Remove.
So guys, my voice will be fine by now, right? Thank goodness I checked it. Otherwise my voice would have been like that for whole hour, right? Thank goodness. Let me check it once again. I hope it is back to normal. So guys, well, you can tell me if you have preferred the the eeny miny mo type voice, chipmunk's voice. So I would have let that stay. I would prefer that as well, right? So I wanted to virus size range. So they range in size from about 20 to 400 nanometer. Guys, look at this. This is in nanometers, and here we are talking about the resolution of the light microscope, and that is 0.2 micrometer. For example, alright, prokaryotes can be observed, but basically they are usually only 1 micrometer to 2 micrometer in diameter, right? Like they are they can be studied because they are only 1 micrometer, and the range is 0.2 micrometer, right? Just their general shape and major morphological features are visible. Of course, if the microorganism is just 1 micrometer to 2 micrometer, the internal structures are going to be smaller than this, and of course light microscope can go further into that. The detailed internal structure of the larger microorganisms also cannot be effectively studied by light microscope. Like nucleus for some organisms can be studied, right? Like it is not that small. These limitations arise from the nature of visible light waves. Alright, so what is the basic problem in the light microscope that do not let the resolution power like below 0.2 micrometer, and that is the wavelength, right? The smaller the wavelength is, the higher the resolution will be, but the visible light wavelength ends at, the smaller one I think is 200. Wait, I forgot. Visible light wavelength. Range between 380 nanometer to 700 nanometer. Okay, so the wavelength is in nanometers, but the resolution is in micrometers, right? By the way, nanometer is smaller than the micrometer. So, not from any inadequacy of the light microscope itself. Like they are saying, the construction doesn't have problem. The only problem is that we don't have higher energy waves, and visible light has its limit. Electron microscopes have much greater resolution. They have transformed microbiology and added immeasurably to our knowledge. The nature of the electron microscope and the ways in which the specimens are prepared for observation are reviewed briefly. So below are the two types of microscope, the transmission electron microscope and the scanning electron microscope. And they are saying that they are going to explain how the electron microscope works one by one. By the way, these two are a bit different because one electron microscope study just the outer appearance of the microorganisms, right? While the one sees the internal structure of the microorganisms. Let's see which one is which. Electron microscope use a beam of electrons to illuminate and create a magnified image of specimens. Right, so this electron microscope produce magnified images of the specimens. Recall that the resolution of the light microscope increases with a decrease in wavelength. Right, the smaller the wavelength is, the resolution will be higher. It uses for illumination. Electrons replace, right? So the only thing needs to be changed is that wavelength, wherever that wavelength comes from, be it light waves, be it radio waves, whatever waves. But electrons use, electron microscope, as the name suggests, uses the electrons in them. So it replaces the light because electrons have a higher energy. So electron higher energy, and when they collide with these objects, or you can say molecules, they release energy which has even smaller wavelengths than the light waves. So we don't use the electron microscope itself, we use their wavelength or their energy waves that they have produced because of their collision with the molecules in that surrounding area. So electrons replace the light by what? When they are deflected by the collisions with air molecules. The specimen scatters some electrons, but those that passes through are used to form an enlarged image on a fluorescent screen. Alright, so like they indirectly use the electrons. Like the electrons don't have anything. I think I misread that sentence in the previous way. Like they don't use the electrons directly, they just use their energy capabilities, right? So they are saying the ones that passes through the object or the specimen are used to create the image because they have more higher energy, and that's why they are able to penetrate right into the specimen. Or you can say that the specimen which you have put doesn't have a nucleus or something in the middle of it, and it doesn't bounce them back, right? And when there is organelles or something like this in their way, they are bounced back, right? So the reflected ones and the refracted or passed ones, like electrons, matter because it is the blockage in their path. And of course, the way they are blocked and the way some are passed make every image different from the other one, right? A denser region in the specimen scatters more electrons and therefore appears darker in the image since fewer electrons strike that area of the screen. Guys, this is more like what machine do we use like to create the skeleton of our body? I completely forgot what was the name. Anyway, so just the same way as our bones look in that, yeah, X-ray, they use X-ray in that rather than the electrons, right? So why does our bones look like bones and no other organ, like they all look kind of different? When you use the some X-rays shows your organs as well, some shows your only skeleton, and that's because they know what kind of energy is required for it to bounce back from what kind of object. Like the bones are the denser or the densest yeah, you can call them organ in our body. So the electrons, or you can say, what do they use, the X-rays, they cannot pass through it. Like the more energy waves you use, they can even pass through the organs, right? The liver, kidney, things like that, but even they cannot pass through the skeleton of your body. That's why we can see only the skeleton and not the other parts, because they are already being passed through. So the areas in which they are not passed through it and are reflected back or scattered back, that area looks darker, right? While I think in those cases the skeleton doesn't look black, but it looks whitish kind of. The surrounding is black, and that's because they used the reverse, we did study that in the light microscope, dark field image, you can say, like where the background is dark while your image is brighter. I don't know if what I said made sense or not, but well, I'm trying to make some sense out of it. Alright, so they are saying a denser region, the specimen scatters more electrons and therefore appears darker in the image since the fewer electrons strike that area of the screen. These regions are said to be electron dense, right? These areas where electrons are reflected are called as or scattered, the electron dense region. In contrast, the electron transparent regions are brighter. The image can also be captured on the photographic film as a permanent record. So they are saying that these electrons which are passed are used to create image, and the image is captured on what area? Photographic film areas as a permanent record, because you know the pattern that the electron uses to make the image, they are kind of stuck in a place and make a permanent picture. Now table 2.4 compares some of the important features of the light and transmission electron microscope. So they are comparing the light microscope and the transmission microscope. Below we have another picture that compares the SEM scanning electron microscope to the light microscope. Now the TEM has distinctive features that places harsh restrictions on the nature of samples that can be viewed, and by means, what am I talking about? And the means by which those samples must be prepared. So they are saying that the TEM has distinctive features, but the drawback is that you have to be more careful on what samples do you use. There are restrictions to that, and not only sample but how you prepare the sample is only specific. Like in light microscope we don't have that kind of restrictions. We use whatever specimen we want, and we use whatever dye is compatible with that, and we put it on the slide and under the microscope, and that's it. But in TAM, like the restriction is kind of like that in the preparation of the specimen. Like the specimen needs to be like thin layer, or thick layer, I don't know which one is in that one. So, and the specimen, like some microorganisms are larger in size, like, right? So or some are smaller in size, so the transmission electron microscope only want one kind of microorganisms. Guys, wait, I'm still confused. Difference between SEM and TM. Completely forgot which one was for 3D image of the surface to no. Which one sees the outer structure, which one sees the inner structure? I see, it looks like the transmission ones. Which one sees outer structure? Which one? Right. Finally, the SEM makes the outer structure, right? The outer appearance or the morphological appearance of the specimen, while the TEM uses the inner structures. And the thing is, these restriction means the nature of the sample should be smaller in size, right? Smaller, these should be like micrometer and nanometer size microorganisms, because the denser, or it doesn't serve the purpose of the larger one. By the specimen preparation, it means that you have to make a thin layer of the specimens, and there are some other chemicals that can be used to fix them, so it doesn't block the way of the electrons, right? And that's because the TAM uses the inner structure, study the inner structure. So that's why it needs this thin layer, right? Guys, wait, I'm a little bit by my cat, my sister's cat. Since electrons are deflected by the air molecules and are easily absorbed and scattered by the solid matter, only extremely thin slices, 20 to 100 nanometers of the microbial specimen, can be viewed in the average TEM. Yeah, right. The reason, he did explain in the coming lines. They are saying that you need to use the thin slices of the specimen, and the reason is why. Such thin slice cannot be cut unless the specimen has support of some kind. The necessary support is provided by plastic. Right, even the material, the slide which you used, is made up of plastic. After fixation with chemicals like glutaraldehyde or osmium tetroxide to stabilize the cellular structure, the specimen is dehydrated, guys. The water content is kind of removed with organic solvents such as acetone or ethanol. Complete dehydration is essential because most plastic used for embedding are not water soluble. Right. Like they need to stick the microorganisms to this plastic, and the plastics are not water soluble. like means the attachment doesn't work on plastics with where the water quantity is high. Why do I do this? Next, the specimen is soaked in the unpolymerized liquid epoxy plastic until it is completely permeated. Now, when you are done with these kind of things like dehydrated, thin layer, then the specimen is soaked unpolymerized liquid epoxy plastic. Like you soak the specimen in this plastic, the name is given, until it is completely permeated. You make it permeable. No, what does permeated mean? Spreads through. Right, it's permeable, like it makes it permeable, like pores are made. Then the plastic is hardened to form a solid block. I think this permeated, making it permeated makes it easier for it to stick to the plastic. Thin sections are cut from this block with a glass or a diamond knife using special instrument called as ultramicrotome. Ultramicrotome. So they are saying the block like plastic mix specimen that you created, how do you cut thin sections from that? They are saying that you do it by ultramicrotome, a glass or diamond knife. Let's look at the picture. How does it look like? Because I think it's a machine. They said it's a knife. Okay, so this is ultramicrotome. This is diamond knife. This. Alright, so this one is diamond knife. So it is stuck to an even bigger machine, and you actually bring the specimen near it for it to cut it. Like it's almost invisible. Wait here. This is the knife and this is the specimen. I think these kinds of things make sense only when you see it in real life. Like images don't help much. Alright, I see. Just looking from this girl. So the cutting is done under the microscope. Right, that was what I was asking. Like how are you going to cut something that's not almost, that is invisible? So you do it under the microscope. As with the bright field microscopy, cells usually must be stained before they can be seen clearly. The probability of electron scattering is determined by the density, atomic number of the specimen atoms. So they are saying that the scattering of electron is determined by the density, and by density you means the specimen's atoms, because electron is so small in size, they go even further than the larger apparent organelles like the nucleus or this and that. They go towards the electron protons type of level. Biological molecules are composed of primarily atoms with a lower atomic number, right? HC and O, and I think it's because the higher the electronic density, they are probably going to be reflected back. And the organic matter, the specimens are organic, right? So of course they have higher amount of hydrogen, carbon, nitrogen and oxygen, but they have lower atomic numbers, and electron scattering is fairly consistent throughout the unstained cell. If you don't stain them, so the scattering is almost same because they all are low atomic numbers, right? So the scattering is not that much different. Look at their atomic number. C is 6, N is 7 and O is 8. Therefore, specimens are prepared for the observation by soaking thin sections with a solution of heavy metal salts like lead citrate and the uranyl acetate. So that's why you need to make it different, so the scattering becomes different, and you use heavy metal salts for that. The lead and the uranium ions bind to the cell structure and make them more electron opaque. Opaque means the electrons cannot pass through them, thus increasing the contrast in the material. Right? This is done to make more contrast rather than the similarity between the atoms. Heavy osmium atoms for the osmium tetroxide fixative also stain cells and increase their contrast. Like the lead and uranium ions are not the only ones used to stain them. They are saying heavy osmium atoms, like where do you get it from? Osmium tetroxide fixatives. You use it to stain as well to make more contrast. The stained thin sections are then mounted on the thin copper grids and viewed. After you are done with staining, then you mount it on the tiny copper grids. Let me see how they look like. Okay, so they look like this. Two other important techniques for preparing specimens are negative staining and shadowing. Right? So negative staining is where you color the background. Like normally we stain the specimen that we use, but in negative staining we stain the background and leave the specimen as it is. In negative way, they already explained it. The specimen is spread out on a thin film with either phosphotungstic acid or uranyl acetate. So this is the stain. Just as in negative staining for the light microscope, heavy metals do not penetrate the specimen but render the background dark, whereas the specimen appears bright in the photograph. Negative staining is an excellent way to study the structure of viruses, bacterial gas vacuoles, and other similar objects. Like bacterial gas vacuoles, they are almost transparent, so if you make the background darker, they almost look visible, like brighter. In shadowing, a specimen is coated with a thin film of platinum or other heavy metals by evaporation at an angle of about 45 degrees from horizontal, so that the metal strikes the microorganisms only from one side. Okay, so you make the specimen make the shadow only from one angle. Usually shadow can be made from any angle, right? And by shadow they means the picture, the image that you get it is a shadow, right? It is a shadow, kind of shadow. So the platinum or other heavy metals which you coat the specimen with, they are able to make a shadow only from one angle, and that is 45% from the horizontal. Means you start from this line and you go only till 45 degree, half of 90 degree, right? Yeah, so the metal strikes the microorganisms only by evaporation. Okay, sorry, it was a little bit here and there. So they make the metal strike the specimen from only one angle, so from only 45 degree from the horizontal, so that the metal strikes the microorganisms only from one side. In one commonly used imaging methods, the area coated with metal appears darker in the photographs, whereas the uncoated side and the shadow region are created by the object is light. So now that you have coated only one angle of the specimen, what happens then? So they are saying the area which is coated with metals appears darker in the photographs because it reflects the electron, while the uncoated side and the shadow region created by the object is light. Like, wait. This is the specimen, and for example, wait. This is the specimen, and let's say this is horizontal line, and if you look at the lines, this must be 45 degree, right? So you bombard this area of specimen with the electron or with the heavy metals or platinum, and this area becomes darker. So the electrons that attacks this side are deflected back or reflected back. So the image that you get from on this side is darker. This area is darker. But the remaining areas, like this area which is uncoated with the heavy metals, this becomes brighter on this side. This technique is particularly useful in studying virus morphology, prokaryotic flagella, and DNA. Like, this is the technique used to study the tiniest and tiniest structures in a cell that can be, for example, DNA, flagella, and the viruses. Of course, viruses are not that big. Here are the diagrams. The first one is a comparison of Rhodosperulum, rubum in phase contrast light microscope. So this is a light microscope, right? The A1. As you can see, these two are the same things. Both are Rhodosperulum rubum. But one, look at the comparison. This is light microscope, while this is electron microscope. Here you can just see that this is a right curvy structures. But when you go into electron microscope, and specifically TEM, right, transmission electron, you see the inner structures. They are saying that the photosynthetic membrane vesicles looks like we can see the vesicles, right? And this is the nucleoid region. Look, the density makes every shadow a bit different. Like, look at these linings between the vesicles. They are even darker than the nucleoid region. And yeah, a transmission electron microscope negatively stained T4 bacteriophage. This is negative staining, where you can clearly see that the background is darker while the virus itself is lighter. Look, you can even see the legs, that is so thin. The hair, tail, and tail fibers. Wait. Electrons replace light. As I completely stopped this, didn't read this. They can be focused much light as in thin light microscope, but their wavelength is around 0.005 nanometer, approximately 100,000 times shorter than that of visible light, because the visible light is 380 nanometer, I guess, while this is 0.005. Look at these zeros after the decimal point. So therefore, electron microscope have the practical resolution roughly 1,000 times better than the light microscope. With many electron microscope, points closer than 0.5 nanometer can be distinguished. So the limit was 0.2 micrometer for the light microscope, and there is a limit is 0.5 nanometer. And the useful magnification as well as over 100,000 times. The magnification is that much higher. The value of electron microscope is evident on the comparison of the photographs. The above diagram that this is, we will see what this is about. A modern transmission electron microscope is a complex and sophisticated, but the basic principle behind its observation can be readily understood because they are completely the same with the light microscope. The only thing that is different is the electrons, right? A heated tungsten filament in the electron gun generates a beam of light that is then focused on the specimen by condenser. Since electrons cannot pass through a glass lens, the donut-shaped electromagnets called the magnetic lenses are used to focus the beam. Guys, in the last area, they just in the light microscope, they used a condenser of simple objects because the light doesn't need that much to stop it from passing through something. But electrons are a different story. To change their trajectory is a different thing. It cannot be done easily by placing just an object or opaque object by stopping them. The way to direct them, because even if you stop them from going somewhere, like for example, this is the area from where the electron beams are coming, right? You might stop it here at this area and you might think that they will go in straight line from now on, but no, that is not the case. The way the electron works are like, as soon as they pass from this area, they are going to scatter once again. Like, this is their nature to go out because they have so much extreme high energy, they cannot be stabilized. So that's why we used magnetic condenser. We electrons, if you know, are negatively charged, right? So they are affected by the magnets. They do produce a magnetic field. So you place these magnetic condenser, even though they looks like they are not doing anything, but when electrons are passing through it, they automatically becomes in a straight lines, right? And the more closer you place the magnetic fields, or you can say the more stronger the magnet is, the more condensed the light will be, the more closer the beams will be, the more narrower beam you will get out of the electron microscope, right? And yeah, the former thing is just the same, that the electrons are collide with the molecules, and then we take the electrons that are passed through the object. Remember, the difference between TEM and SEM is, in TEM we take the image from the electrons that are passed from the specimen, passed through the specimen, while in SEM, scanning electron microscope, we take the electrons that are deflected from the object. So that's why the image that we get is different. In TEM, the image we get is for the inner structures, the morphologies, while in SEM, the image that we get is the outer appearance, because it is the reflection. They only get to go through the surface of the objects. They haven't gone past through it. That's why the image only carries the outer appearance. The range of the light microscope, while the range of electron microscope. So if you take the scale 0.1 nanometer, and we said that the resolution is 0.5 nanometer, right? And you take it 100 micrometer, so the light microscope will go only to 0.2 micrometer. 0.2 micrometer exactly here, right? 0.2 micrometer comes here, like this is 1, and if you go, this is 0. Consider this 0 micrometer, or 100 nanometer equals to 0 micrometer. If this is 0 micrometer and this is 1, so 0.1, 2, 3, 4, 5, 6 to 10 points right below between. So this is 0.2 micrometer, the light microscope. While when we go for the electron microscope, it goes below to 0.5 nanometer. Is this 0.5? 1, 2, 3, 4 here. Wait, they are showing 0.4. Well, it can be a little bit different looking because it's just a diagram. They did said that it is 0.5 nanometer. Now let's see what are the range of the organic substances that goes along with these scales. So the one is the epithelial cells, and they only goes to the 10.12, 10.2 micrometers are the epithelial cells. So light microscope can easily see them. Your red blood cells are just a little bit smaller, and that is 1. Wait, this is, if this is 10, Wait. If this is 10 micrometer, then automatically this is 8 micrometer, and this one is 12 micrometer. Okay, sorry. I was considering the points. Then this one will 100 nanometer, 10 raised to power minus 9, and it will be 10 raised to power minus 7 and not 6. Oh, this is not the same. Where would my math go? 100 nanometer is equal to 10 micrometer. 10 micrometer. No. 10 raised to power minus 7 is the answer that we get. This is so stupid. 100 nanometer is 10 raised to power minus 9 meter. Now I need to do math. This is more like 10 raised to power 2, right? So the answer we will get will be 10 raised to power minus 7, while the micrometer is minus 6. This is minus 7. So this will be 0.1 multiply 10 raised to power minus 6 meter. So that will be 0.1 micrometer. 0.1 micrometer, right? So looks like this area is 0.1 micrometer. The heck is wrong with them for making it 0.1 and the remaining scale as 1 difference, and this is point difference. No wonder 0.2 comes here. So this area is 0.2 micrometer, the ultimate range. This area is 0.1 micrometer, or 10 raised to power minus 1 micrometer, the same thing. Wait, so then the 10 nanometer will be 1 micrometer. No, what am I talking about? How can it be bigger number? Ten multiply 10 raised to power minus 9. Oh, okay, so we are going larger at that, more like smaller. So this is 0.1, then this will be 0.01 micrometer. I like to do strange things, okay? This is important. 1 nanometer means 1 nanometer. Okay, so we get it. So the mycoplasma goes around 0.2 micrometer. Typical bacteria is from 1 micrometer. Typical bacteria, guys. Mycoplasma are the smallest bacteria. So they are around 0.2 micrometer, the ultimate range of the light microscope. The viruses, the proteins, amino acids all goes below in the nanometer range, and the atoms are even smaller than nanometer. Smaller than nanometer. Alright, we are done with this. Like, there was nothing specific in that. They are just showing that the light microscope can go up to this area, to 0.2 micrometer. The electron microscope can go to 0.5 nanometer, and that is that. And they are telling us the range of the cells that or the organic matter that we can see under which kind of microscope. Like till mycoplasma, we can see it in the electron microscope, in the light microscope as well, like epithelial cells or red blood cells and the typical bacteria, right? But below, like the viruses, the proteins, amino acids, like the atomic level structures, we can see only under the electron microscope. Look at this. This is a typical transmission electron microscope, right? This area, the wire, you can see there. From there, when you connect it to the electricity, the electron beam is passed through this, or you can say, what do you call it, gunned? I don't know. You laser sharp projected, the beam is projected from this area. Like this area, I haven't been in contact with the electron microscope, so I don't know what area is which from just the outer appearance. And this area is the specimen holder. This area is the fluorescence. I mean, the image you can see is here, right? The permanent image. Is everything being done inside this? Yeah, I think the specimen, you put it here and then put it inside the electron microscope. This is not typical light microscope where you can see the image out. The TEM will disclose the shape of organelles within the microorganisms if the specimens are produced by freeze etching procedure. So not only DNA flagella can be seen by TEM, the organelles can be seen by the TEM as well. And if the specimen are prepared by freeze etching, the ads are so ugly. First, cells are rapidly frozen in the liquid nitrogen and then warmed to -100 degrees centigrade in a vacuum chamber. Guys, liquid nitrogen is up till -96 degrees centigrade. Why do you warm it even below the -90? Wait, oh, okay. Liquid nitrogen is -196. Am I right? I remember it was just 96. Nitrogen temperature. Okay, so it is -196. When you want to warm up the specimen, do it slowly, because if you suddenly change the temperature from -196 to 0 or 37 or you can say 27 as a room temperature, they will break. The inner structures of the cell will break. It will die. So you have to do it slowly. So they are saying that you can do it by changing the temperature from -196 to -100 in vacuum chamber, right? Like, so it is not in contact with the outer temperature. Next, a knife that has been pre-cooled with the liquid nitrogen. Again, when you wanna study the specimen in the freezing state, that's how you are going to do. That's what they are telling us. So they are saying you have to cool the knife at -196 degree. Fractures the frozen cells. When you use a temperature that is higher than -100, or you can say lower than -100, like it is more colder than -100 degrees centigrade where your cell is. When you use that -196 degrees centigrade knife on the -100 degrees centigrade cells, they fractures, which are very brittle and break along the lines of greatest weakness, usually down the middle of internal membranes. You can even cut the middle membranes with that knife. So the specimen is left in the high vacuum for a minute or more so that some of the ice can sublimate away and uncover more structural detail. It's not like you are going to change the temperature, but -100 temperature you can like change, or you can say the cells may be a little less covered with the ice than before when they were at -96. So it like cools down a bit at -100, even though it is not by a lot. So when it is a little bit cooled down, or no, not cooled down, warmed up, the structures become more closer to their original structure shape, not in a frozen state. We all know that the freezing do affects the structural details, right? So finally, the exposed surfaces are shadowed and coated with a layer of platinum and carbon to form a replica of the surface. So again, the thing is, you cover it because the heavy metal can deflect the electron more in different angles rather than the atoms itself. The atoms in our own cells, like CHO, are all of the same levels, are all of the same level atomic numbers. So we cover it with platinum or carbon to make the scattering more contrast. After the specimen has been removed chemically, this replica is studied. Well, okay, so that was the purpose. The other purpose is, it looks like they are telling us that you can change, or you can remove the specimen, right? You can remove the specimen that you studied, because the specimen in electron microscope, it is going to get warmed up whether you want it or not. So for you to preserve the specimen as it is, you just need to make a mold of it and then take the structure, the specimen out of it, and put it again in the liquid nitrogen to cool it down and store for a long time. And then you study that replica that you made from the platinum or carbon atom, and provides a detailed three-dimensional view of the intracellular structures. An advantage of the freeze etching is that it minimizes the danger of artifacts because the cells are frozen quickly rather than being subject to chemical fixation, dehydration, and plastic embedding. Artifacts means, I think, the cell damage, because chemicals and plastic embedding, these kind of things do damages the cell. And they are saying that the cells are frozen quickly, like the process that the time that you have to go through the chemical fixation, dehydration, plastic embedding, and then cutting it with the ultra microtome kind of thing, they takes a lot of time, and a lot of errors can come in that. But the freeze etching is a simple process. You make this cell freeze at minus 196 degrees, then bring it at minus 100 degrees centigrade in a vacuum, and then cut it with a minus 196 degrees centigrade knife, and that's it. That's all, or not all. Then you cover it, make a replica of this cell by using the platinum or carbon atom, and then you study it under TEM. Rather than when you have to stain them, you have to embed plastic and put chemicals, and then you have to put more chemicals to make it dehydrate. Then you have to put more platinum or things like that to change the contrast or things like that. So it takes more time. So they are saying it's easier to do more advantage for us to do the freeze etching method. But not everyone has liquid nitrogen. Now towards the scanning electron microscope. Transmission electron microscopes form an image from the radiation. As I said, the scanning electron microscope is used for studying the outer structure of the cells rather than the inside structure of the cells as TEM. So the scanning electron microscope works in different manner. It produces an image from the electrons released from the atom on object surface. So there are two types of electrons which is present in the electron microscope. One is it is passed through the object, and the passed through the object electrons we study, or we take image from that in the TEM. But the electrons that are scattered from the surface because of their high density, we take these reflected electrons and make an image, and that image is the outer structure image, and that is the scanning electron microscope procedure. We take the reflected electron microscope. So the SEM has been used to examine the surfaces of microorganisms in great detail. Many SEMs have a resolution of 7 nanometer or less. looks like the TEM has more resolution power than the SEM. TEM has 0.5 nanometer while the SEM has 7 nanometer. Specimen preparation for SEM is relatively easy, right? TEM needs a lot more work because it is used to study the internal structures. This one doesn't need as much work. And they are saying in some cases air dried material can be examined directly, right? Like in the previous case, dehydration was done by chemicals. In this case, it can be done like air drying is enough for the studying. Most often, however, microorganisms must first be fixed, dehydrated, and dried to preserve the surface structure and prevent collapse of the cells when they are exposed to the SEM's high vacuum. Guys, why do you think the vacuum is used in the electron microscope? The thing is that the electrons can be deflected by any molecule in the atmosphere. So you have to use the vacuum so that the only material or the only molecules in that area is of your specimen and nothing of the air remains, so that you know completely that these electrons are reflected or refracted by only your specimen. That's why vacuum is needed, to completely get rid of any other molecules rather than your specimen. So they are saying usually we can study the air dried specimens under the SEM, but it is more likely that we need to fix it, dehydrate it, and dry to preserve its structure and to prevent the collapse because of the vacuum. The sudden change in the atmosphere, the microorganisms are sensitive to anything. Any drastic change can lead to microbial cell death. That's why the sudden changes are not preferred with any procedure. So that's why you have to fix it, dehydrate, and go through all the procedures so it doesn't collapse from the vacuum. Before viewing, dried samples are mounted and coated with a thin layer of metal to prevent buildup of an electron charge on the surface and to give a better image. Because electrons are negatively charged and our cells have the atoms that can react to the electrons, so that's why we don't want the electrons to get built up on our surface, right? So we use the metals. That is that as well, and of course because to make more contrast. To create an image, the SEM scans a narrow tapered electron beam back and forth over a specimen. Back and forth means that it can come from above and it can come from below the specimen to study overall structure of the cell, not just the upper surface, right? Surface atoms discharge a tiny shower of electrons called the secondary electrons. Guys, now what? There is another not complex, but there is another thing in the deflection of electrons. They are saying when when a beam strikes, when electron strikes an area, the surface atoms, your atoms, discharge a tiny shower of electrons because every atom has the electron. Every atom has it, right? The orbitals, it has electrons, whether less or large in quantity. So when the initial electrons came from the beam strikes the surface, the electrons in the atoms of the surface release their electrons because the energy is disturbed kind of. So the electron which is not strongly bound, they get out of their orbitals and they are known as secondary electrons. Like they knock out the electrons. The beam electrons knock out the surface electrons, and these are trapped by special detectors. Now you don't want the electrons to be trapped in that area. You want to get rid of these electrons, so you make more space for the upcoming electron microscopes, right? Not microscope, for the upcoming electrons. So that's why there is a special detector and they trap these electrons, and the pattern and the area with which it collapses or reflects or hit the detector is all calculated in the detector to make an image. Secondary electrons entering the detector strike a Scintillator. What is scintillator? Causing it to emit the light flashes that a photomultiplier converts to an electrical current and amplifies. Looks like the scintillator is an object which causes the light when the electron binds with bounds with it, no, strikes with it, right? The scintillator is a machine which creates a flashlight when the electron strikes with it, and that light is not that much high in the amount, so photomultiplier increase or amplify the light that is produced and make it change it into the electrical current, and the electrical current which is produced is further amplified. The signal is sent to a cathode ray tube and produces an image like a television picture which can be viewed or photographed. So above this point there is no image, right? But the pattern with which it is captured and with which it is produced, the pattern with which it strikes make an image, and then you combine the patterns. The computer has its own machinery mind to make an image out of those patterns, and that pattern image is now viewed and photographed. The number of secondary electrons reaching the detector depends on the nature of the specimen surface, right? If your surface has less chance of the atoms that have more strictly bounded electrons, they have less chances of releasing the secondary electrons. When the electron beam strikes a raised area, a large number of secondary electrons enter a detector. Raised area, guys, like a mountain area. In contrast, fewer electrons escape the depression in the surface and reaches the detector. Why is that? That the lifted area, the raised area, reflects more secondary electrons. It may be because the electron attack is stronger on the raised area, right? And I think it's because they are more lonely, like more less bounded to one another than the inside, while the area which is regretted, no, what was the word that is used here? Depression, like the area which is depressed, like well type area. First the electron reaches slowly into their area, or you can say the probability of reaching higher number of electrons to that area is less, right? And they are at the end, like they are the end point of electrons reaching them, so the energy of the electrons might be disturbed, or they are more strongly bound to one another. Thus raised areas appear lighter on the screen and depressions are darker. Right, the areas where the reflection is high, that area looks lighter, brighter, while the area where the reflection is lower appears darker. A realistic three-dimensional, guys, see the difference? In TEM, the area which is being reflected had the darker image, right? Because we were studying only the pass-through electrons. So in those cases, the reflected electron areas were showed as darker. But in this case, SEM, the area where the electrons are reflected appears brighter. The more reflection, the more brighter it is. The actual in situ location of the microorganisms in ecological niche, such as human skins and the lining of the gut, also can be examined. So this is the end. We are going to study just the diagram, and so in situ is on the site location, right? The ecologist that studies the microorganisms in their natural habitat. So they are saying that such as human skin or these kind of microorganisms which are present on the human lining or gut can also be studied by the SEM. So this is just the example, you can say. Now they are comparing the light microscope with the so they are not comparing with the SEM. Well, transmission and scanning is almost the same, except that you take the two different types of electron. One is scattered and one is passed through. So light microscope, first difference is light microscope we use the lamp or any source of light, right? This one is electron gun. We use electron gun to produce electron beam. Now there are condenser, and their condenser is a lens, right? And there the condenser is a magnet to make the electron go pass through it in a beam like shape. Now they are passing through the specimen. Both work the same way, but there is an objective lens, while there is again a magnetic condenser, or you can say condenser as well. Why is that? Because in electron microscope we don't see the image by our eyes. In a transmission electron microscope, the fluorescent screen works as our eye, so and they don't need any lens because they studies the pattern of these electrons rather than the light captured, directly by the lens as well. In lamp we use our own eyes, and that's why we need objective lenses for magnification. Here, because we use the lamp light, so that's why we use the lens, because it is needed for our eyes to see the resolution. But here our eyes are not needed, and even if we see with our eyes, we cannot see anything because these are electrons and not actually the light. We can only see the light whose wavelength ranges in the visible light region. If you see at the electron, its wavelength is way, way, way smaller than what our eyes can understand, decipher. So after they pass through it, the specimen, it creates an image. The image is passed through the ocular lens in the case of light microscope, while in this case the image is passed through the, again with a magnifier type magnet, not magnifier. There is a magnet as well. Like the light was handled by the lenses. There the electrons are beams are handled by the magnetic condensers, and it goes to eyes, and this one goes towards the screen and then our eyes. Let's see general characteristics of the light and transmission electron microscope. Highest practical magnification, that is only 1000 times or 1500 times. Well, this one is 100,000 times, 1000 times and 100,000 times. Best resolution is the smallest, like the limit resolution is 0.2. You cannot see below this one, while there it is in nanometers, 0.5 nanometer. Radiation source, like what light or what beam or what wavelength is used from where. Here it is visible light, while in transmission electron it is electron beam. Remember, they are using transmission electron again, because the SEM and the TEM is almost the same, except their use of the image. How they manufacture the image is a little bit different. That's why it doesn't matter whether there is SEM or TM. Medium travel. The medium here is because the light, we don't have to worry about it striking with any other molecules rather than our specimen. That's why the medium is air and there is high vacuum. We don't want any other molecule rather than our specimen. Types of I use again the rather. Types of lens is the glass. There is electromagnet, no lens. Source of contrast, differential light absorption, like there is the light absorption works, right? While there is the scattering of electrons. Contrast means how they elevated the object, which area is upper, lower, and that's you use to make an image. Focusing mechanism is adjust lens position mechanically. Adjust current to magnetic lens. Okay, so this is magnetic lens. I have never heard of a lens that is magnetic. I just thought that these were condensers. Methods of changing magnification. Switch to the objective lens or eyepiece. add current to the magnetic lens. Again, wherever the lens is, there will be magnetic area. Specimen mount, glass slide, while there's metal grade, usually copper. Specimen shadowing for the TEM. Guys, we did study a shadowing technique, right? So this is for which is this diagram: Proteus, mirabilis, node flagella, and the femora. We did said that this shadowing is done for smaller structures like DNA and things like that. So there we use the flagella studying, while the T4 coliphage, this is a virus. We also study this in shadowing techniques. Is there? Oh my goodness. Freeze etching technique. Guys, we did study another technique, freeze etching. And let's see how does this work. We did study it, how it works. Number or letter A. This is the knife edge, plane of fracture, nucleus, vesicular structure, nuclear envelope. What am I studying? So this is the cell. This is cell. That's its plasma membrane. That is its vacuoles or vesicle structure. And this is nucleus, nuclear envelope. When you put it in front of a knife edge, it completely cuts this cell, like in the middle of it, like here, this area. Fractured faces means the faces are appearing, exposed. The area that is exposed when you cover it with the platinum and carbon, shadowing direction is 45 degree. You cover them with 45 degree. If you look at this, the area that is more prone towards the 45 degree are covered more densely, while with the area that is not at the 45 degree are covered lessly or more like not at all. Like look at this area. This is not in the face of 45 degrees, so this is not covered at all. Neither this one. Now when you are done with the covering, you leave it to sublimation. Sublimation is done so just as I was thinking, what the heck. Fractured faces means because the cells were freezed, right? So that's why fracture is used. And then sublimation, we leave it for a little bit time for warming up so that the ice or the ice is sublimated, means directly converted into gas, so our surface is more apparent. And then we use the covering part. When we cover it, then replica, then you put another so you do double coating. First is just the platinum and carbon, just carbon, and then the platinum carbon mixture to make a replica, so that you can take the cell out of here and you just need that outer shell like structure to study under the TM or EM. A frozen eukaryotic cell is fractured with cool knife. Etching by sublimation is depicted right. Shadowing with platinum plus carbon and replica formation in D and E. The scanning electron microscope structure. Now they are showing me the diagrams when I'm done with this. So this is vacuum system, secondary electron gun. Like electron is passed through here, then the magnets make it more condenser lenses, means they make the electron beams go wherever we want. This is a scanning coil, scanning circuit, cathode rays, tube for viewing cathode rays. Why? Secondary electron specimens detector. There is a detector, photomultiplier, and then the cathode ray tube and photography. So we already studied what these kind of things are. Examples of freeze etching. So this is how this specimen looks like. Look, it doesn't even look alive because it isn't. S is the outer. Where is S? OMCCMOM. Here is S. This is the outer membrane, the cytoplasmic membrane. Because it is fractured, so it doesn't matter if it is fractured in a good way or bad way or in a regular way. It is just cut, and every part of the cell is exposed up till the nuclear membranes. OM is the cytoplasmic membrane, CM is the cytoplasm itself, and C is just saying that this area is 0.1 micrometer. Scanning electron micrograph of bacteria. Christie spira, a spirochete from crystalline style of oyster. Ostrea virginica, the axial fibers are blah blah blah. So this is Staphylococcus aureus. This is scanning electron microscope, so we can only see the outer structure. While this is Christie spira, a spirochete, because it is spiral. And this is also just the outer structure, because look at this, even this roughly shaped like fibers kind of things, periplasmic flagella, can be visible on the structure. And wait, this is, don't talk here, light microscopy, CSL composite of all the sections, CSL 3D construction, Z cross section. What is this? No wonder I wasn't getting what they were talking about. This is not related to today's topic. So this is it. We are done.